Hello, everyone. So today we are going to talk an important topic in machine learning, and it's about comparing machine learning classifiers. Now, all of you, train different classifiers on a daily basis on your different data sets. But then the key question is, how good are these classifiers? How confident are you about the results that you're getting from these classifiers? What what if we train more than one classifier on one or two or more data sets, and what we can infer from the performance of these classifiers on these data sets? Many times you will see in in research papers that somebody will say, oh, my classifier is 90% and it performed 2% better than the previous method. So the question is 2% significant enough or not? Or is your classifier working more or less the same as the classifier that you're comparing against? So um, when we train these machine learning classifiers, there are two key questions that we ask, or we should always ask. First is that how can we assess the expected error of a learning algorithm on a problem? So when you are testing your classifier, then how confident you are that your algorithm will perform at a certain rate. So when you say, sorry, that your algorithm has a 90% performance class, it could be accuracy, it could be AUC, it could be any other performance metric. For simplicity, let's take accuracy as the performance metric and error as the error rate. So error is 1 minus or 100 minus the performance, right? Or so if you're saying that my classifier gives 10% error, so what does that mean? How much confident you are that it will be consistent 10% uh, when I run this classifier in the wild on a test set. And the next question is, given two classification algorithms, how can we say that one algorithm has less error than the other one? So the example that I gave, that if you are obtaining 90% and the other classifier is getting 88%, so how confident you are in saying that you are doing better? Now, before we move on, we must understand that the comparison of classifiers never happen on the training errors. And part of this we covered in our previous lecture on the cross-validation, where we talked about this training set, validation set, test set. The papers that I shared with you, I think they have used this validation set and test set interchangeably, but basically validation in our context means the test set. So we should never use the training errors to compare in the algorithms, because you can artificially overfit your training data. And training error, apart from, training error doesn't tell you much apart from the fact that you may be doing overfitting. So training error, never look at the training error when you are comparing the algorithms. We already talked about cross-validation in our previous talk. Sorry, can you hear me now?
Yep.
Yep, I can see you.
Okay, so in the previous talk, in my previous talk, I talked about cross-validation as a means of testing classifiers. Um, However, a cross-validation may or may not be possible in many cases. So one of the simplest cases that you may have done it already, that you split the data into two sets. So let's say a training or and a test set, right? And then you train your algorithm on your training set, and then you test it on the test set, right? And that, let's say, partition is arbitrary. You can do it 70-30, 80-20, 90-10, whatever. right? Now, what is the problem with that approach? Why do we think that this is not a good idea? First is that your training or test set may be a very small portion. So the test set that you are testing is a very small portion. It may contain certain exceptional instances. It may contain noisy instances. So the performance that you're getting is not a good representative of the actual test set, right? Now there can be other factors that may influence, such as if you're using neural networks, then different initial weights in a neural network, even if your training data is the same, just by changing the initial conditions, you may reach at a different answer, right? So that is why it is important to understand that just doing one partition is not a good approach. So to resolve this situation, um, we can create multiple partitions. So cross validation is one of the way where you partition the data in a particular way, and we discussed in detail before that you create these folds, and then you train on n-1 portion of the data and then test on the nth, and then you repeat it n times. So that's one way. Another way is of creating multiple partition is that for the same data, randomly you choose, let's say, 80% of the samples, um, and then 20% for testing, and then you choose another 80% and choose the remaining 20%, and you do it again and again and again, right? So that type of method, also known as bootstrapping and all. So you can also do that. But now the question is that whether we are doing that kind of approach of cross validation, um, are we like, can we confidently say that how good my classifier is trained? So the basic reason of running this kind of analysis is to eliminate the effect of chance or randomness that is present in the data, or some uncontrollable things, and then obtain conclusions which we can consider statistically significant. So that is the basis of doing these statistical tests on these machine learning classifiers. Now, from this point onward, it's going to be a little bit mathematical, and normally my slides are not so wordy, but I think it is, but in today's presentation, I use lots of words and equations because it is important to understand what actually is happening, and unless we see the mathematics, we cannot understand. So before we move on to the actual statistical tests that are employed to test these classifiers, let's do a very quick recap. And in the paper that I shared with you, you might have already gone through this. So I'm just going to go very quickly from this. So I'm going to talk quickly about the hypothesis testing. So let's say if the mean and standard deviation are known, mu and sigma. So the null hypothesis, let's say our null hypothesis is that the mean of this distribution is equal to some mu naught, right? Now, this is some arbitrary choice. So if this is your null hypothesis, and m is some point estimate of mu. Point estimate is some number that follows that distribution of mu. Then we can reject h naught if m is too far away from mu zero. So this is the basis of rejecting or accepting a null hypothesis, and this is going to occur again and again and again. So it is important that we all understand and are on the same page that what is a null hypothesis, and there can be different types of null hypotheses. I'll only talk about two null hypotheses here, and what do we mean by accepting and rejecting them. Okay, so in this scenario where both mean and sigma are known, we fail to reject the hypothesis with some alpha level of significance if mu naught lies in this range 100 into 1 minus alpha significance percent confidence interval. So if your value is within this interval under root n m minus mu over sigma, then we say that this follows a normal distribution, and and we reject this null hypothesis if it falls outside. So this is a two-sided test. As you can see, this goes from minus z alpha by 2 to z alpha by 2. So if the value of your statistic is outside, then we reject the hypothesis. If it is inside, then we fail to reject or we accept it. So this is a two-sided test. Now there are two types of errors that we see. First is if we reject when the hypothesis is correct. This is called type 1 error. In machine learning and classification, you hear a lot about false positive, false positive, false negative. So this is very similar to that concept. So when you reject um, the hypothesis when actually it was true, right? So that is called the type 1 error or the alpha. So this alpha level of significance occurs again and again. So it is important to understand what alpha means. And alpha is the amount of error that you are allowing uh, to and to I mean this is the amount of error that in lay terms you can say that you're okay with. But then you want to assess, given my alpha equals to 5% or 1%, whatever my confidence that I want to keep, uh, how does my classifier perform, right? So we'll see this alpha again and again, and this is type 1 error. And alternatively, if we fail to reject the null hypothesis when the true mean mu is unequal to mu 0, then this is a type 2 error. So the difference, the opposite error. We can also do a one-sided test. So as I said, this when we check whether when the null hypothesis was if mu equals to mu naught, then this is a two-sided test. We can also do a one-sided test where we only check whether the mean mu is let's say less than mu naught, right? Less than equal to mu naught. So you're just looking in one direction. You're only trying to say whether your mean is less than or not. That's it. When you're doing equal to, then you have to look do the two-sided test. So in this test, in the one-sided test with alpha level of significance, it defines the 101 minus alpha confidence interval bounded on one side, in which M should lie for the hypothesis not to be rejected. And we fail to reject if, um, uh, uh, you know, if this statistic that you compute under root M minus mu naught over sigma, if it is within that interval, or we reject if it lies outside. So two simple things to understand: when the null hypothesis, when we are testing a situation like mu equals to mu naught, then it is a two-sided test. When we are looking at greater than or equal to, then it is a one-sided test. And this will be repeated again and again in all these tests. Second scenario is when you have a known mu, but the variance is unknown. So in that situation, we use the sample variance instead of the population variance, okay? And this actually, interestingly, follows a t distribution. So if you have n samples, the statistics looks like under root m minus mu over sigma with, so this follows a t distribution with n minus 1 degrees of freedom. So let's say the situation is your null hypothesis is mu equals to mu naught. H1 is the alternative hypothesis, and we fail to reject at significance level alpha the same formula if it is within this interval, or we reject it if it is outside the interval. But here you see the difference is that it follows a t distribution. Earlier it was normal distribution. So this is also a two-sided test because we are checking mu equals to mu naught. Okay, so enough of this testing, hypothesis testing, but I think it is important to understand because this is the concept that we'll be using in future tests. Now, coming back to the actual test. So let's say you have, so I'm going to start from very basic examples and then we'll build up on that. And maybe you will relate because you might have done some of these, you might have trained your classifiers in these ways, in these manners. So maybe you can situate your work and see which test applies to you. So first is the binomial test, and it applies to a situation where you have a single training and a single validation or a test set. What do I mean by that is, let's say you have a data and then you split your data into, let's say 70 or 30, okay? You train your classifier on the 70% and then you test on 30%. I have seen that a lot whenever ask people to build classifiers. That's the first thing that they do. That's the first thing many people do unintentionally. Or if you don't know anything about, uh, uh, or maybe if you're a beginner, if you don't know much about classifier evaluation, this is the first thing that people do. They train on some bunch of data and then they test on one sample, right? If you have millions and millions of records, then maybe that is fine. But if you have a limited data, you should understand that with limited data, there are more chances of errors and the technique not working in the real world. So this is I have seen this so many times, like this is the default setting that many of us do. We choose some trained data. Now that can be arbitrary, and then we test on one sample, okay? So now let's say P is the probability that the classifier makes a misclassification error, okay? And XT, let's say, denotes the correctness of the classifier decision for every sample. So let's say you have T equals to 1 to N. So you have X are basically the samples here. So XT is, so X1, X2, X3. So let's say these are the samples. So they denote the correctness of the classifier, and they follow a 0, 1 Bernoulli random variable that takes 1 for error with probability P and 0 for correct prediction with 1 minus P. Okay, so you have different samples that you're testing, and for every for every sample you are basically counting whether it is doing correct or incorrect classification. So then you can count the total number of errors by summing all of these xt's. Okay, so x equals to sum of all the xt's. Now in this case, my null hypothesis is that p is less than or equal to some p naught, and that I can decide. So what I'm trying to say here is that I will always perform, let's say, worse than 90%, or sorry, p is the misclassification rate. So I can always say that I will always get error less than 10%. So let's say this is, so P naught is your 0.1. So this is your null hypothesis. Now you want to test based on your data, how good you're doing. So from the Bernoulli distribution, we know that the probability that a classifier commits J errors out of N is given by this expression. And we reject H naught when probability of seeing X equal to E errors is more or less, of seeing X equal to E errors or more is very unlikely. And we sum over all the errors basically. And we check if it is less than alpha. If it is less than alpha, then we reject the null hypothesis. So this is a very simple test. And another test, if you are still following the same pattern that you have one training set and you have one test set, then you can also do this approximate and normal test. Um, and normally it is not advisable, but it is good to know that this type of test also exists. So for large n, so if you have large n and small p, and so x is normally distributed with mean np and variance np 1 minus p, and then you can calculate the z statistics, and you accept this if it is less than z alpha, or you reject it if it is greater than z alpha. Now for every z value, so alpha is, like as I said, is the level of significance, or is the amount of errors that you allow, or you're willing to accept. So you can actually find, and you might have already, I mean, you may already know about this, that for every value of z, you can actually find what it corresponds to. So sorry, for every value of alpha, you can find the actual value of z. In back in the days, they used to provide these tables, t tables and z tables and chi-square tables at the back of these math books. But there are formulas as well. You can find it online. So for example, for the z value at 0.05 alpha is 1.96. So what you do is, when you run this test, you find the statistic using this formula, and you simply check whether it is greater than 1.96 or not. If it is greater than, then you reject the null hypothesis. If it is less, you accept it. It's very simple. Now, this formula works well when n is not too small, so n has to be large, and p should not be very close to 0 or 1. Now, what happens if sorry, it should be p naught. It's not p. So the p naught should not be very close to 0 or 1. What happens if p becomes 0? Then the denominator will be undefined, right? And the same when p naught is equals to 1, then the denominator becomes 0 and the whole expression becomes undefined. So there are some, like as I said, limiting issues for that, and there are some rule of thumb then, that n into p naught should be greater than 5 and things like that. Basically, it is limited by, if you have limited number of samples, then this is not a good test to do. Okay, now let's go to a more, I would say, stronger test, and a more popular test as well, and maybe you heard of it already. It's called the t-test. And the t-test, what t-test says is, within the context of these comparison of classifiers, if you randomly choose training data multiple times, you choose 80% or whatever percent for training, and then for testing, and then you choose another randomly for training, and then the remaining for testing, and you do it multiple times, let's say k times. So for every run, you will get an estimate of error estimate pi, right? So pi is p1, p2, p3. So let's say you do this 100 times, so you will get 100 pi estimate for each of these runs. It is a very simple test. So what we do here is, we just find the mean and the standard deviation of all the PIs, and then we put that into this formula, under root k into m minus p naught over s. And this follows a t distribution with k minus 1 degree of freedom. So if you have generated 10 samples or 100 samples of your training data, let's say k equals to 100, then this will have 99 degrees of freedom. If you have generated 10 samples, then you will have 9 degrees of freedom. So then you reject the null hypothesis at a significance level alpha if this value is greater than t alpha comma k minus 1. Alpha is the significance, k is the number of samples that you have generated. For example, for k equals to 10, the t statistics, the equivalent t statistics at alpha equals to 0.05 and 9 degrees of freedom is 1.83. And we'll see some of these things in action when I run the code later on. So this is a very simple test. You find all the estimates for all the partitions, for all the, and then you just find the mean and standard deviation and find the t statistic. Now, so far we were looking at one classifier only. When you're not comparing with any other classifier, let's say your classifier was the only classifier in the world, and then you were either testing on one partition, or if you're running your classifier on the same data set multiple times. But normally that does not happen. You always have to compare your classifier with some other classifier to get an intuition if you're doing good or not in statistical terms. So what I'm going to do today is I'm only going to consider a situation where we are comparing two classifiers. That's it, because when we have multiple classifiers and multiple data sets, then the statistics changes further. So we'll limit the discussion today to two classifiers. Okay, so if let's say you have two classifiers, classifier 1 and classifier 2, and you only created one training and one validation set, or a test set, right? So you're not doing a cross validation. Like, so the kind of situation we were looking here during the binomial test and the approximate normal test, that you only have single training and single validation. But now what you're doing is you're running two classifiers on these. So what can happen? So these are the four situations that can happen, that N00 are the examples misclassified by both classifier 1 and 2, right? N01 is the examples misclassified by 1, but not by 2. N10 are the examples misclassified by classifier 2, but not 1. N11 are the examples correctly classified by both 1 and 2, right? That's how you do it, right? You create these confusion matrices. It's very simple, and in this expression, n absolute value of n01 minus n10 minus 1 whole square over n01 plus n10, it actually follows chi-square distribution with 1 degree of freedom. So you reject the hypothesis that the two classification algorithms have the same error rate at significance level alpha if the value is greater than chi-square alpha, comma 1 degree of freedom. This is very simple. So what you do is you run these two classifiers, you find where they differ, and then you put those numbers in this formula, and that formula follows the chi-square distribution with 1 degree of freedom and alpha significance. So for example, for alpha equals to 0.05, this value is 3.84. So if the statistic that you obtain after putting in this formula is greater than 3.84, you reject the null hypothesis, otherwise you accept it. So this is a very simple, easy test to compare two classifiers when you have only one partition. Now things get a little bit complicated here. Not so complicated if you have understood the cross validation aspect. So let's say now you have two classifiers and you're doing cross validation on both of them. But it is very, very important, and I think I emphasized that in my previous lecture as well. When we do cross validation, we have to make sure that both the classifiers see the same training set and the same test set. Because if the training set is not the same, you cannot compare those classifiers. So basically then you're comparing apple versus oranges. To compare apple versus apple with apples, it is important that both the classifiers, or if you have more classifiers, they should all see the same training set and the same test set, of course. So I'm not going to talk more about cross validation because you already know. If you don't, please go back to the previous lecture. So let's say you have these two classifiers and you perform cross validation on each one of them. And PIs are the estimate of misclassification error for each of those folds for classifier 1, so PI1, and then PI2 are the estimates of misclassification error for classification 2. So for every fold, what we do is we find the mean, um, sorry, we find the difference between those estimates. So for example, let's say we are in fold 1, and we pass this test set, okay? And let's say classifier 1 gives me uh, let's say 0.1, and then classifier 2 gives me 0.12, then I find the difference, 0.1 minus 0.12. So this is how, so we go actually fold by fold. So we find the difference between these classifiers at every fold. So what is the difference at fold 1? What is the difference at fold 2? What is the difference at fold 3, and so on? And once, so then PI will actually contain the difference of performance at every fold. And then afterwards, it's very simple. Once you have PI, you find the mean and standard deviation, and is very similar to this one. So in this case, in the case of t test, we had this P naught here. P naught is actually 0. So you want to, because your null hypothesis is, yeah, I actually forgot to say that. So what actually you want to test here? So what you're testing is that in an ideal situation, you want to see whether the two classifiers are working very similar or not. So your null hypothesis is that their difference is not significant enough, or this difference of mean is actually 0. That's what you're testing. So that is why instead of P naught, you have M minus 0. And so you put in this formula, you get under root K into M over S. And this is T distributed with K minus 1 degrees of freedom. And you reject, again, if it is outside this interval, and you accept it if it is inside it. And a sample example for T, 0.05 over 2, so which is 0.025, and with 9 degrees of freedom is 2.26. Now, this only tests whether there was, whether there, how do I say, like this, this paired t-test actually, because we are doing it in pairs, so we are finding the difference of each of the pairs, right? So it tells us whether there was significant difference between these two classifiers or not. But we can also test, like, if classifier 1 has less error than classifier 2. This H naught mu equals to 0 only tells you if there is a significant difference between the, it. I think somebody's mic is on. Can you please mute yourself? So this test only tells us whether there was a significant difference between them or not. It does not tell you if classifier 1 performs better than the other. So this is a very important distinction to understand. And if you want to test if classifier 1 has less error than classifier 2, then you have to do a one-tail test, and your null hypothesis will change accordingly. Okay. All right. So now coming to the more interesting part is the 5x2 cross-validation pair test. So we understand this in k-fold cross-validation, we can choose whatever k we want. We can do a 10-fold cross-validation. We can do whatever fold cross-validation. But then now they have these standardized tests for 5x2 cross-validation. So what it means is that you perform two-fold cross-validation 5 times. So how do you do it 5 times? You randomly you randomize the data, right? choose half for training, half for testing, and then choose the other half for training, half for testing. That's one run. Then you randomize the data again, and then you repeat the process, and then you randomize the data again. So you do it 5 times. So, and then Pij is the difference between error rates on fold j and j equals to 1 and 2, because there are only two folds on different replications, which is 1, 2, 3, 4, 5, right? And then they define the mean and standard deviation of each replication as it's very simple. So pi and si square, and then the null hypothesis is that the two classifiers have the same error rate as we saw before. And Pij can be treated as approximately normally distributed with zero mean and unknown variance. So, and then Pij over sigma is approximately unit normal. So, and then SI square over sigma square has a chi-square distribution with 1 degree of freedom, and their sum also has a chi-square distribution with 5 degrees of freedom. And you can formulate and you can find, put in the previous formula, and you can obtain this T statistics with 5 degree of freedom. And you reject the null hypothesis that two classification algorithms have the same error rate at significance level if this value is outside this interval. Okay. I mean, it may sound complicated, but it is not. What you're doing is you want to, at a high level, what this test is doing, what it is doing is that you're trying to see if your classifier is consistent. Is your classifier consistent if I change the order of the data? And you do it 5 times. It's very simple. So you are actually trying to test the robustness of your classifier. Now, there are some issues with this test, and one of the issues that it assumes that these P1 and PI1 and PI2 are independent normal, and each of these SIs are independent. But they are not independent because it's the same data, and you're drawing these samples from the same data. So the assumption that this test makes is like very strong, which does not actually hold. Another important issue is if you look in on this formula, this t equals to pi1 over sigma over under root m over 5. You can, I mean, this, the choice of numerator is arbitrary. You can put any of the pi's. I is the number of replications, right? So you can put uh, any of the PIs. In total, you have like 10 PIs, right? Two for every fold, there are two PIs, and there are 5 folds. So there are 10 PIs. So you can put any of those, and then you will get 10 statistics in this case, right? So numerator is arbitrary in this, and it can lead to 10 statistics. Um, so the next test, and which is I think the last test for today, is this 5x2 cross validation paired F test. And what this F test does is it actually combines all of these 10 statistics together. Like what it is going to test is it will go into all of the cross validation, and it will check how good you are doing across all these different cross validations. Okay. So what this F test does is it combines the results of these 10 possible um, statistics. So Pij over sigma follows normal distribution, then Pij whole square over sigma square follows a chi distribution, and their sum is chi squared with 10 degree of freedom. So what you do is you um, you actually find the sum of all of these Pij, like square, uh, uh, sum of squares, and then you place this numerator in the previous formula. What I mean by this previous formula is here, and we get these statistics. That is the ratio of two chi-square distribution variables, um, and two variables divided by their respective degrees of freedom is actually f distributed. So if you have two chi-square distribution, two variables which are divided by their respective degree of freedom, so they follow a f distribution. And in this case, it is with 10 degrees and 5 degrees of freedom. So you just replace these values in the formula, and you get these statistics. And this rejects the null hypothesis again if this is greater than this f alpha, and 10 comma 1, where 10 and 5 are the degrees of freedom, and for alpha equals to